And I'm going to bring up the PowerPoint here. So we're going to minimize that. We'll start the PowerPoint. All right. And we're going to start with the scientific method and lab reporting. No need to write this down. Again, you might be thinking, this isn't much of a science class. We haven't written anything down. But this, again, is still just a discussion. When it comes to the scientific method itself, I have a handout that shows the scientific method and how I want lab reports. That's on Google Classroom. It's all right there. No need to write it down. We will be getting to talking about chemistry next week on Monday, and then we will start taking notes concerning chemicals and things like that. This is still process. So what we want to talk about today is scientific method and lab reporting. And this sometimes scares students away. Sometimes students are afraid of what we would call a lab or scientific method. And there's nothing to be afraid of when it comes to the scientific method, all right? And that's because we are all scientists deep down. We always have been, ever since we were born, we have been a scientist. And I'm going to explain to you how we've been a scientist. We use the scientific method every day. Every day of our lives, we very quickly run through the scientific method whenever we have to make a decision about something. You may not realize that you're doing it, but you are. You're doing it all the time. And let me explain how that is. So the true scientific method, the thing that you get taught, is that you've got a handful of things that you've got to go through. Things like asking a question. We often call that the purpose. Things like making a hypothesis. All right, we're going to talk about those things. But essentially, every day of your life, whenever you've got to make a decision, you do it very quickly, but you start by observing something. You see something, you observe it, and then you might question it. And in your mind, you're thinking, I just saw that. Does that make any sense? Or does, what is that the case? Once you've asked the question, you come up with an answer very quickly in your mind. You have, I think it did that because of this. You create a hypothesis. You make a quick guess of what you think it is. Then what you do is you automatically do something to test what you're thinking. You ask someone a question. You maybe change the settings on your phone, or maybe you have an issue with your computer or an issue with something, so you change something. You do Control-Alt-Delete. So you try something. That's essentially conducting an experiment. If what you did fixes the problem, in other words, you get it fixed or you solve it, then you say to yourself, I've got it. I figured out what was wrong. If it doesn't fix it, you have to say, my guess was wrong. I need to make a new guess so I can come up with fixing the problem. Now, scientists do that in a very formal manner. We talk about very specific things. We're going to do a quick little experiment at the end of the lesson today, and if we don't get to today, we'll do it tomorrow, where we're going to look at the volume of a gas. Here I've trapped some air in here, and the pressure it exerts. And I'm going to change the volume by, you're going to change the volume by squeezing the syringe, and you're going to see what the pressure does. We call this in physics the pressure-volume relationship. Sometimes it's called Boyle's law, named after the scientist who came up with the first idea. But I'm going to make you guys have a guess at some point in time. Well, when we make the gas smaller and we squeeze it, this is going to happen to the pressure. Now, most of you already have an idea. The pressure is going to do something, and you already are formulating an idea in your mind. If I squeeze that gas into a smaller volume, the pressure will, what do you think? What's the pressure going to do if I squeeze that gas into a smaller volume? Go up. There's a hypothesis. You could think the pressure might go down. Whatever, that's your hypothesis. So we do it as scientists in a very specific manner, but you do it as regular people every day without even realizing it anytime you encounter something that doesn't quite go right. Let's talk about it. Here's a classic one. Let's say tomorrow, for some reason, I couldn't come in, and you got a supply teacher. Right away, You see the supply teacher, and you got, oh, this is good. I got a supply teacher. And right away, you ask the question, is this guy a pushover? Boom, first thing in your mind. Let's see if he's a pushover. Let's conduct an experiment. What do you do? What do you do? What's your move? What's your supply teacher move so I can warn them when they come in? What's your move? Yeah. You don't do anything, you just behave? Nice, so you let someone else do the experiments. Good move, so you can't get into trouble. What's your move? How do you test whether the supply teacher is a pushover?
Me?
Anybody, I don't care. What do you got?
I don't know. I just kind of like screw around.
You start to screw around. Okay, I'm going to screw around, and I'm going to
Like
see.
not every person. I just
Yeah, well, yep. Oh, change seats. Change seats. That's a good one. You might even, 2 minutes in, you might say, can I go to the bathroom? Yeah. Whoa! Woo! Everybody in the room goes, yeah, baby, this is awesome. We got a free-for-all for 75 minutes, right? That is the scientific process. Even though you don't realize it, you're doing it. You see the supply teacher. You ask the question, is this guy a pushover? I think this guy might be a pushover. Let's do an experiment. Can I go to the bathroom? Yeah, I don't think so. Oh, crap. And everybody, put your phones away. Oh, no. Right? And then you conduct an experiment. I'm going to try one more thing. I'm going to try sneaking the text. Oh, I got away with it. Oh, I'm going to keep sneaking the text. Oh, no, I didn't get away with it. All right, this guy's not a pushover. That sucks. And you've got a conclusion. The guy's not a pushover. Okay? But that is the scientific method. You do it every time you are presented with a new situation. Your four-wheeler doesn't start. Turn. Right away, you got to come up with a hypothesis. For the question, you got to come up with a question. The question is, well, you sometimes jump to the hypothesis. The question is, why doesn't the four-wheeler start? That's what the question is. What might be a hypothesis? What could be the problem? Yep. Spark plug. Is that the first thing you check? You get the wrenches out and pull in spark plugs first?
Well, pull the choke and see if it goes and check the gas.
Check the gas! Check the gas! You normally would go through, the easiest one is to check the gas. Okay, got gas. Right. So then you're going to choke it, right? And then you're not going to get any fire. So what you're doing every time is a little experiment, right? So conduct a hypothesis. Might be out of gas. Experiment. Nope, there's gas in it. Go back, change the hypothesis. Choke it, right? It might need choking. Nope. Flood, smell fuel all over the place. Okay, not choking. Might be misfiring. Yep.
You could have a broken spark plug.
Yeah, so you could have a faulty spark plug. Next, you're going to pull the spark plug. Check for spark. So every one of those things that you do is using the scientific method. It is doing a quick little experiment, all right? Even sometimes I find when I get to the spark plug part, it's like, oh, man, I don't want to get a spark plug. You try to clean it. You work on that one for a long time. And then if you still can't get it to fire, then at that point, I'm like, oh, bring it into the shop. Like, I'm not that good with that type of stuff. So once I get to know spark, if it's sparking, and I'm still not getting fire, then it's probably a compression thing or something crazy like that. But every time you are encountered with a situation that you are not accustomed to, you do a little experiment. One more. We'll do one more. Your friend did not reply to your text. That drives you crazy, right? So what do? Hey, you send a hey, right? Or you send, maybe it's your girlfriend or whatever. Hey, what you doing? Whatever you do. And then nothing. A minute goes by. 2 minutes go by. And this is where, you very often create the wrong hypothesis and you get yourself into trouble, right? Because your hypothesis is, they're ignoring me. What? And you send some kind of a mean text. And in the end, their battery, what could have been, their battery could have been dead or they were out of the signal. But right away, you're, right? But you keep doing these experiments. Why are you ignoring me? Still nothing. Holy cow. Could they be ignoring me that much? Maybe their battery's dead. Maybe their battery's dead. I'm going to have to wait for this experiment. This is going to be a long experiment. Until I see them, I can't tell whether their battery is dead. So again, in your mind, you're using the scientific process. every time. So like I said, every time you encounter something that you are not accustomed to, your brain will automatically kick in. You'll quickly ask yourself a question. What's going on? Why aren't they replying to my text? Okay, let's do let's do an experiment. Maybe I can send them an email through email and see if they're, and then you go through a whole bunch of stuff. And then eventually you have to go and talk to them. Hey, what are you doing? Why didn't you reply? Oh, I couldn't, man. I had a really evil supply teacher. Took all our phones away. Who knows? All right? So what I'm trying to get across to you is that the scientific method is not a scary thing. We use it all the time. We use it every time we encounter something that we are not accustomed to. Okay. Graphing review. I am going to want you to write this down, but I'm going to get you to write it down in our lab booklets. So I'm going to hand out these lab booklets, and I didn't think you guys needed a full lab booklet, so I cut the lab booklets in half. So some of you get the nice place to write your name on it, and others of you don't. And those of you who have the benefit of sitting at the front of the row, you get to decide which ones you want. That's up to you. 1, 2, 3, 4. But put your name on it, and and I'll tell you what to put as a title. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3 for now. Okay. So what I want you to do is put your name on it. If you have the option of putting your name right where it says name, that's awesome. If you don't, just write your name in the blank space up there. Put your name on there somehow, and you're going to call this the SNC 2P lab book. Okay? You're going to call that the SNC 2P lab book, all right? And you can put that kind of wherever you'd like, all right, if you've got that. Excellent. So you can open that lab book up, and I do want you to write down that slide, okay? I do want you to write down that slide on that first page. So what I'm going to do now in this portion of the lesson is go over graphing, because very often in science, we have to graph our information in order to get an idea, all right? So that says graphing review. I apologize that it doesn't fit on there very nicely. Let me check if my smartboard isn't doing anything right now. Why am I not able to, oh, back up. Am I able to write on this? Oh, I am. Okay, so the smartboard is working. Perfect. Now, in my little discussion about what scientific method is, I didn't talk about variables. In all of the examples that we talked about, I think there's really only one of the things that we could have did as a variable, and that's the example of choking the engine on a four-wheeler. Some of you aren't, I know that some of you are not mechanical and maybe have never had to run a four-wheeler or choke an engine. But when you choke an engine, what you do is you pull a lever that then restricts the amount of air that comes in, and then that brings in some extra fuel, and it allows that combustion to take place. And you can do that on a varying degree. You can pull the choke lever out a little bit, or you could pull the choke lever out halfway, or you could pull the choke lever out all the way, right? So I guess if we were talking about the choking the engine, that would be a variable. How far do you pull the choke out in order to get that engine to start? So that would be a thing that we're testing, and we're changing it. We're going to pull the choke out, see if the engine starts. With every experiment, there are 3 types of variables. And in actual fact, this term, controlled variable, it's really not a great term, because if we're keeping it constant, it's really not a variable. That's the thing that we don't change. We want to keep constant so that when we're studying it, it doesn't affect anything. You can write the example as well at the bottom. That's what we're going to test with our little experiment in a moment. Here, I'm going to let you guys write, and then I will talk in a minute once you're done. Now those lab books, they've only got one hole in them now because I cut the other hole in half. I could punch new holes in them, but I'm hoping that you can keep them in your binder with that one hole. We will be using the lab books whenever we do labs. We're going to use it to write in our observations, and if we have to make a graph, that's where we're going to make our graphs by hand. Because I'm using Google Classroom and we're going to do a lot of typing on the computer, if we do a lab report that needs a graph, we'll take a picture of the graph, right? And then we'll put that into it like that. But you'll have the graph in your lab book, okay? So let's again talk a little bit about variables. And I want to get away from this idea of the engine and choking the engine. Let's go back to the little experiment that we're going to do here in a moment. That's going to look at how the pressure of a gas, so there's our pressure gauge, changes when we change the volume of the gas, okay? So you can see here, here's the example. How is the pressure of a gas affected by a change in volume of the gas? So variables are the things that are being tested. And you'll notice that in our experiment, I'm going to adjust something and I'm going to measure something, okay? The independent variable is the thing that's being changed. It's what the scientist is adjusting, okay? When we graph it, we put the independent variable along the x-axis so that we can say, this is what we changed as we move left to right. The dependent variable depends on what we did in the independent variable. The dependent variable is the thing that's being affected or is changing because of what we've changed. We graph that along the y-axis up and down so that we can see how this thing is being affected as we change the thing. Here's the example that we're going to do, and this is going to become the purpose of our first experiment. How is the pressure of a gas affected by the change in volume? Tell me, out of these two things, which is the independent variable? Which is the thing that we're going to manipulate and change as the scientist? Which of these things, which of these two things, the volume or the pressure, is the independent variable, the thing that's being changed? Which one do you think it is? This gentleman here, I'm going to get his name, had a thought. Riley? What do you think, Riley? Which one are we going to be changing? We're going to be adjusting the volume. The volume is what we're going to be manipulating. That makes the volume, all right, the independent variable. I'm just going to put here underneath it, independent. Do the same thing. The volume is the independent. What is being affected by that independent variable? What is the dependent variable? And again, I'm getting names. Eric? Oh, the gas. Careful, I need more details about the gas. What is it about the gas that's going to change? The pressure of the gas. The pressure of the gas is the dependent variable. Okay? Now, there are other variables that can change the pressure of a gas. Not just the volume, but other things can change it. And we don't want those things to affect our experiment. So we need to keep those constant. We need to keep them controlled. You won't find it in our example, but we can think about it. What do I have to keep the same as I do this experiment? Yep, Eric? The amount of gas that's in it. If I were to let more gas in and out, it's going to change the pressure every time. Excellent. The amount of the gas is a controlled variable. We must keep that the same. What else do you think can change the pressure of a gas that we have to keep the same? Yep? Ooh, that's interesting. The size of the syringe. I really don't know if that affects that. We could do an experiment to see whether that does. That wasn't what I was thinking of, but the diameter of the syringe, I'm not sure whether that's the case. Would our experiment be different if we used a smaller syringe? I don't know. That's a good thought. But we better keep it the same for this one, and then we could try another experiment with another one and keep changing it and see if it does. I don't know, but it could be. I'm thinking of one other one that affects the pressure of a gas greatly. You might notice this in the winter versus the summer, looking at your tires. Yep. Air density, would air density change? That's an interesting question. Potentially. That wasn't what I was thinking of, but potentially that's the true statement. Air's density would change with this. It's going to change with this as well. The temperature itself. If I were to do the first couple of trials in here, a hot room, and then go into Mr. Petrus's air-conditioned room and do the experiment at the end there, it would change my experiment because I would change that. And that's what controlled variables are. Okay, excellent, good. So what we want to talk about now is how are we going to graph this information, all right? And don't worry about this, you're not writing this down. We got all kinds of different types of graphs. You would have done different types of graphs in grade 9, circle graphs and bar graphs. You do this type of thing in maybe geography where you're trying to express percentages of things like populations. In science, we're not really too interested in graphing this way. We like line graphs because we want to see trends. We want to see what the line is going to do. So we're going to go work together here in a moment to do a line graph. All right. On the next page, write these graphing techniques, and then we're going to make a graph together as a team. So then we're going to do a graph together, and then we're going to get into doing this experiment with the gas. Yep? You can't read any of it? If you open up Google Classroom and you go to today's lesson and you click on the PowerPoint, it's going to be right there. Scroll down, that same note is the same that's on the PowerPoint. So you can always do that instead of looking up there and follow along. Okay? So if you have issues with eyesight, in the past we used to, move you to the front and make fun of you, but you can now still, you just look at it there. So you can always do that. Whenever I do a note, it's going to be on Google Classroom. So you can always do that, okay? All right? Good graphing techniques. Graphs must have a title. Titles are easy. Don't get crazy creative, right? I find sometimes when biology is doing a graph, they'll have a great crazy long title. A graph representing the mating rituals of a gray whale during the period of June to July. Like, wow, that's a crazy long title. Like, in chemistry and physics, keep it simple. If I'm graphing pressure and I'm graphing volume, pressure versus volume, keep it simple. Put the data in a chart. We're not going to do this for the practice. I'm going to give you a chart. But when we do our little experiment, you're going to have to create a chart. Try to figure out what the independent variable is. Try to figure out what the dependent variable is. That's going to determine where you're going to graph it. Place the independent variable on the x-axis. Place the dependent variable on the y-axis. Each axis must be labeled. And I'm going to add something to that because I'm just seeing it. I'm thinking we need to add it. Each axis must be labeled with units included. Please put the units with whatever you're putting there. All right, so if we were measuring centimeters for some reason, we were graphing centimeters, in brackets you would put centimeters. Oh, and I was going to demonstrate using this camera, but I might try to do it right on there, but we don't have our data. No, I'll do it on, I won't do it on the video. I'll do it on I'll demonstrate it with you because I'm gonna project the data. Plot the data. Put your dots. I'm not a fan of necessarily a point protector. Some teachers like to have you put a little triangle around each of the dots or a little square. I don't get too excited about that. If you just have a dot, that's fine. For line graphs, draw a line of best fit which follows the pattern of the points. Sometimes the line of best fit is a line. It's an actual line. Sometimes it's a curve. Sometimes there's a definite curve to the work. But we don't join the dots. We don't want to bouncing around. We want to get an idea for what the trend is. Okay, so once you're done that, I'm going to give you some data. And I actually have a handout on Google Classroom, but I'm going to use the data that I have on my next slide. I think I do. I'm going to come back here for, oh no, I don't have another slide. So I'm going to have to go to Google Classroom's handout, and you'll have to do the same. So if you're done writing that, you can go to Google Classroom, and one of them is graphing techniques, and there's some graphing practice problems, and we're going to do one of those together, okay? Now, as you're writing here, I am going to stop the video recorder because I'm done the recording of what I want to do. So I'm going to just click save.